Hi everyone, this is Maverick Paul, the chemistry guru. Now in this video, we want to discuss the suggested solution for 2021 A-Levels H2 Chemistry Paper 1 Question 12. So question 12 goes something like this. I have an equilibrium is set up in a vessel at constant temperature and atmospheric pressure according to the following reaction. So we have calcium oxide plus carbon dioxide in the gaseous state to give me calcium carbonate. Enthalpy change for the reaction is minus 178 kJ per mole. The vessel is attached to a plunger which can alter the pressure inside the vessel. At a certain time t, the plunger is pulled out quickly to lower the pressure and then is released to allow the pressure to slowly return to atmospheric pressure. So go back to the original atmospheric pressure. Constant temperature is maintained throughout this process. So the question is asking which graph shows the change in the rate of the forward reaction during this pressure change. So we have four options, A, B, C, D, and maybe let us just briefly talk about it. Involving A, at the rate of the forward reaction, at T it decreases sharply, then slowly goes back to the original state. Involving B, at T, the rate of the forward reaction decreases sharply and then stays low. For B, involving C, the rate of the forward reaction increases sharply, then return back to the original rate. And involving D, there's no change in the rate of the forward reaction at all throughout the entire process. So which of these four graphs will be the correct one? Now, the topic tested in this exercise is under chemical equilibria. So what we have to understand first is there any change in the position of the equilibrium when you're imposing this change, when you're lowering the pressure? And how is the position of equilibrium affected? And how does it affect the rate of the forward reaction at time t? So let's consider the change imposed. I'm lowering the pressure sharply at time t, which means that the total pressure of the system decreases and the partial pressure for carbon dioxide will also decrease. Now involving my three species here, calcium oxide, carbon dioxide, and calcium carbonate, only CO2, it is a gas. So therefore, only the partial pressure for CO2 is affected, and the partial pressure for CO2, which is the reactant, it decreases. Then according to Le Chatelier's principle, the position of equilibrium should shift towards the left-hand side. Because according to Le Chatelier's principle, if you have a change imposed that the system feels, it will try to oppose or counter the change that is taking place. So we can treat the system as a stubborn fella. It always wants to go back to its original state. So if you're imposing a change to it, usually it doesn't like it. So you just try to resist the change. It wants to revert back to the original state. So if you lower the pressure, system will not like this decrease in pressure. What you try to do is you shift the position of equilibrium towards the left-hand side. You try to increase back the partial pressure for carbon dioxide by trying to form more carbon dioxide, because if I can form more CO2, then the partial pressure for CO2 will increase. So essentially, this is what the system will do. Position of equilibrium shifts left. Basically, it is favoring the reverse reaction. It also means that it is disfavoring the forward reaction, because we want to link it to the rate of the forward reaction. So if it likes the reverse reaction, so it doesn't like the forward reaction, if it disfavors the forward reaction, the rate of the forward reaction will decrease. So we do expect a drop in the rate of the forward reaction. So if I look at my four options, A, B, C, D, we can eliminate C. C means that it's favoring the forward reaction, rate of the forward reaction increases, which is not true because carbon dioxide, it is the reactant. If I decrease the partial pressure for CO2, position of equilibrium should be shifting towards the left-hand side, and it should disfavor the forward reaction, and the rate of the forward reaction should drop, shouldn't increase. So C, it is not true. Now option D is also not true, because option D is suggesting that there's no change in the position of equilibrium, there's no shift in the forward or the reverse reaction. So we can eliminate C, you can eliminate D, so now it is between A and B. Will the rate of the reaction decreases and then later it goes back to the original state, or will the rate of the forward reaction decreases and it stays low, stays that way? Now, we have to look back at the question, Because the question mentioned that we are returning the pressure to its original atmospheric pressure at constant temperature. So if the pressure goes back to the original pressure, then the conditions will be exactly the same as before. So we do expect the rate of the fall reaction to return to the original state, because based on the same temperature and based on the same pressure, the partial pressure for your CO2 should be the same as before. So therefore, the rate of the fall reaction should also go back to the same as before. So we do expect the rate of the fall reaction to return to its original state. So between A and B, A should be a better answer. It decreases, but later it's going to go back because everything will revert back to the original state. Involving B, it would be the correct answer if the question mentions that I'm decreasing the pressure and the pressure stays low. That means I have a change in pulse and the change is there. So we will expect rate of the fall reaction to decrease, and it maintains this lowered rate of fall reaction if the pressure remains low. But since the question tells me that the pressure is going back to the original state, so the rate of the fall reaction should also go back to the original state. So between A and B, for this exercise, A will be a better answer. Alright, so that was the discussion involving question 12. If you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.